Welcome to the presentation of a study on the formation of mega sand waves in estuaries and its effect on the design of shipping fairways that I undertook together with my co-authors Holly Watson and David Taylor. The study was for a planned phosphate export terminal in Guinea Bissau. Guinea Bissau is located in West Africa and the project site is along the Geba River. This is a fairly unique site in that ocean-going vessels are able to sail into the estuary over a distance of almost 200 kilometers, kept open by strong tidal currents. The tidal range at the project site is about 5 meters during spring tide, and the site is about 20 kilometers east of the capital Bissau. And Bissau has a port for smaller vessels, and the new terminal is designed for largest vessels with a draft of 10 to 12 meters. And the objective of the study was to plan a navigation fairway along the river for laden vessels departing from the terminal without the need for dredging or frequent bathymetric surveys. At the start of the project, a bathymetric survey was conducted to verify the depth of the navigation fairway and to look for better fairway route options where possible. The area hasn't been surveyed since the 1960s, so it would have been a huge operation to survey the entire estuary. The navigation route is 180 kilometers long and the river is about 20 kilometers wide on average. Therefore, the survey focused on the projected navigation route and additional lines were surveyed to look for other route options. There are a few shoals here close to the terminal, and the fairway goes around some rocky outcrops here near Ponte Bernavell. In the offshore area, two route options were surveyed that go over bars here, here, and here, and the northern route was identified as the slightly better option. Looking closer at the survey data over the offshore bars, these large bed forms or sand waves were discovered. They were not present everywhere, but along certain stretches here over the bar in the southern route and on the offshore end of the bar here. Well, they were not present over the bar here. These bedforms are highly mobile and can change in position and height. The same sand waves that were observed here may develop over these offshore bars as well. This must be accounted for when planning the navigation of vessels, as it is not feasible to conduct frequent bathymetric surveys. Sediment samples were taken at about 100 sites in the estuary. The most interesting one is the one over here, where the sand waves occurred. The sample consisted of gravelly, muddy sand, mostly fine to medium sand, and the gravel made up of shell fragments. Unfortunately, there were no samples taken along the southern route, where the largest sand waves occurred. We took a closer look at the area along the southern route where the largest bed forms occurred to verify how they may be able to grow. The largest one was observed here with a height of 3.7 meters and a length of 70 meters. A series of other large bed forms occurred here with a height of up to 2.5 meters, and these bed forms are a bit shorter than the values calculated as the largest possible bed forms using the Yellen and the Silva and the Van Rijn formulas. According to the theory, they cannot grow larger than a certain limit that is dependent on the water depth, larger in deeper water and lower in shallow water. The largest observed bed form coincided well with the maximum possible bed form using the Yellen and the Silva formula. It was then decided to add an allowance for formation of megabed forms to the survey over the offshore bars based on the maximum possible bed form height for each water depth using the Yellin and the Silver formula. For the design of the navigation route, the channel was divided into sections with a length of 100 meters, and the highest point in each section was taken as the bed level for bottom clearance, as plotted here. There are two constraining points here and here, and near the terminal and the rocky outcrop over here. In the offshore area, an allowance for mega bedforms was added, as 75% of the theoretical mega bedform height. So the mega bedforms have narrow and high crests and shallower troughs, and we assumed that the crests can be up to 75% and the troughs 25% of the dune height. Then as such, about 3 meters was added to the survey data to provide the bottom clearance level for the offshore bars. There are several components in the Underkeel clearance analysis of a ship sailing along the navigation fairway to make sure that the vessel doesn't touch the bottom or the channel bed. The static position of the keel is defined by the water level and the static draft, and the clearance between the keel and the channel bed consists of the squat, the heel, wave response, and a net underkeel clearance that is added for safety and uncertainties. The water level in our analysis is from tide predictions, which change over time and also over the position along the estuary. Squat is the sinkage of the vessel due to forward speed and was modeled using an accurate description of the hull shape. And this depends on the vessel's speed through water, so also including the current velocity. Heeling, due to beam on or oblique winds, was added using PN calculations and is usually small for laden bulk carriers. Wave response, due to heave, roll, and pitch in waves, was small along the river, but is relevant in the offshore sections due to northwesterly swells especially from November to March. And this was added using response modeling in waves, similar to the squat modeling, using an accurate description of the vessel hull shape. And the net underkeel clearance depends on uncertainties and the risk level, and this was chosen as 1 meter over the rocky outcrop, half a meter over channel beds, which is or sandy channel beds, which is along most of the navigation route, and no net underkeel clearance was added in the offshore sections, since all risk and uncertainty is already included in the Bedform allowance, which was approximately 3 meters, so much greater than a net underkeel clearance of up to 1 meter that's usually added. And as pointed out before, the bottom clearance bed level is the highest surveyed point in each channel segment, and the mean bed level plus 75% of the mega bedform height for the offshore areas. And after taking the water level, the bed level, and all underkeel clearance components, the maximum allowable vessel draft can be calculated. Now these underkeel clearance calculations were undertaken along the entire navigation route and for 1 year of metocean data. Water levels were obtained from tide predictions, and currents were obtained from 2D hydrodynamic modeling conducted for the entire area, for which the grid is shown here. Waves were obtained from spectral wave modeling, and the entire wave spectrum is input to the vessel response calculations. The vessel speed profile over the length of the channel was obtained from a departure passage plan. And this passage plan was designed for 190 meter long Supramax bulk carriers with laden to a draft of about 11 meters. And the vessel leaves the terminal against a flood current, which is safest as it provides the best rudder control. The vessel passes the shallow section with rocky outcrops after about 30 kilometers at high tide. You can see that here. Providing the best underkeel clearance in that area. And it's best to pass also the offshore areas at the following high tide to provide the best underkeel clearance here as well. And to achieve this, the vessel can anchor for about 2.5 hours in an area somewhere here. This has the additional benefit that the pilot is able to rest before navigating the offshore sections. The offshore sections are then passed on the following high tide, and the tidal range is less here, but there's still a benefit to use the tide to negotiate these offshore sections. The total transit time for the 180 kilometer route is about 15 hours, and it appeared that with the inclusion of the mega Bedform allowance in the offshore sections, the offshore bars are constraining, which is shown here in this underkeel clearance plot, where the underkeel clearance is shown positively, and here the bed level underneath. However, we could prove that the vessel can still pass safely at the target draft of 11 meters. In summary, mega sand waves were observed along the offshore bars of the Geba estuary, and the height of these sand waves agreed well with the Yellen and da Silva formula. Upper bound estimates of the dune height based on this formula were then added to the bathymetric survey data, and the resulting theoretical bed profile was used to develop a vessel departure plan. Bulk carriers navigate the outer bars at high tide to allow sufficient underkeel clearance, and the mega Bedform allowance and passage plan was integrated in the underkeel clearance calculations. So I would like to thank you for your attendance and invite you to post any questions that you may have.